Thank you so much for the invitation. I'm so pleased to be here. I just want to get a quick read of who my audience is. So can you raise your hand if you work, if you have a company or a startup that's doing anything related to health data? Oh, good. Can you raise your hand if you actually successfully deployed to multiple hospitals or multiple outpatient clinics? Okay, good. And then raise your hand if you're an investor, you're just generally interested in this area, even though you don't work in it, but sort of from a distance, you watch what's going on. Okay. I'm interested in others of you too. Okay, let me start by giving you an example. So I'm introducing you here to Mrs. Manny. Mrs. Manny is 52 years old. She came to the emergency department. This is at one of the Maryland hospitals. She came in with what looked like a foot sore that seemed like it could be nasty. She ended up staying in the hospital for 22 days. So here's what happened. When Mrs. Manny came in and she complained of her foot and also just generally not feeling well, doctors inspected what was going on. They didn't see any reason for real concern, but she also didn't have great family support. So they admitted her to a general ward. On day 3, however, she starts showing symptoms of what looks like pneumonia. Doctors do the regular checkup. They give her the usual dose of antibiotics, and they think hopefully all will recover. But now on day 6, she starts experiencing tachycardia. For those of you who are not clinicians, tachycardia means your heart rate rhythm has accelerated dramatically. On day 7, she experiences shortness of breath, leading to then what looks like septic shock. So incidentally, death rates in septic shock are 1 in 2. Now, only it is at this point it's really clear that she's in dire need, and they put her into the intensive care unit. So the ICUs are where the most critical patients get cared for. At the ICU, they do everything possible to resuscitate her. But unfortunately, her kidney died, then her lungs start to fail, and then on day 22, she passes away. So what happened to Mrs. Manny was, so Mrs. Manny did receive the right set of treatments while she was in the ICU. The main handicap here was that she received them only too late. What Mrs. Manny experienced is called sepsis. So sepsis occurs because of an infection. So when you get infected, your body releases chemicals to fight the infection. In some fraction of these cases, the chemicals that are released start attacking your organ systems itself. And if the attack gets large enough and is not resuscitated, is not controlled in time, it escalates and leading to organ failure and death. So sepsis is the 11th leading cause of death, leading to more deaths than breast cancer and prostate cancer combined. But here's the catch: sepsis is preventable if treated early. So we have something that is a huge killer. It is preventable if treated early. So then what's the challenge? In practice, with the current standard of care, sepsis is very hard to otherwise diagnose. So there's a study that shows out of Harvard with 93 academic experts, when they were given cases of patients with and without sepsis, the inter-expert agreement around who is and isn't septic was very, very low. So how are we going to think about it? So one big change that has happened in medicine in the last decade is the introduction of electronic health records. Now, every single time a patient enters a hospital or routine clinic visit, the data that is getting, so you have labs and physiology and symptomology, all of this data is getting collected and stored digitally. What this now means is that it's possible to get a much more granular view into any individual's health that was previously not possible to do. And more exciting, this data is available not just for you, but now as we're starting to collect this as electronic health record data are getting collected more widely in more sources, and also through wearables, you're starting to get this kind of data available not for one individual, but millions of individuals, offering an opportunity for us to learn to how to generalize from large populations to care better for a single individual. And so let me tell you about an effort that at Hopkins we started about 3 to 4 years ago on tackling the problem of sepsis, because it was clear it's a large medical, it's an area where it might be possible to do something, to change status quo. And so with my collaborators, we developed what we refer to as a program for targeted real-time early warning for sepsis. Okay, so let me step back and define at a very, very high level. Like, how do we think of, because I think we've, rather than thinking about networks and single architectures, let's step back and think about how do we take some of these problems and we formulate them as, quote, AI problems, right? And also the word AI gets used all the time these days, so let's think a little also about, like, what do we mean by an AI problem, okay? So here's exactly what I mean, whether you call it. So here's how we train a machine how to learn things, right? So here, the first thing we need is we have to define a goal, which we in the field would call an objective function. So we're going to define a goal. So let's imagine your goal was to teach a robot how to walk, okay? And in particular, walk as quickly as walk for as long as possible without falling. That's your goal, okay? So then the next thing we have to do is to define this goal in some mathematically relevant way, and you're going to use some objective function to define it. Next, this robot is going to now try to figure out how to walk, and in this particular case, once it knows that I have a goal that I can mathematically evaluate, I'm going to try a sequence of strategies, and these strategies work in some action space. So in this particular case, if the robot's learning how to move, it has to experiment with moving its joints in certain ways. So it's experimenting with different moves. And each move it tries gets a score. So if the move is helping the robot walk and not fall, it gets a positive score. If the move is causes the robot to fail, it gets or fall down, it gets a negative score. And effectively, over time, as it starts to collect these scores, it wants to take a step in the gradient direction, that is, try to take moves in a direction that tries to maximize its score as much as possible. Now, what I described to you was a scenario where the robot is learning by interacting with the environment. So you have an objective function, you have a sequence of in order to learn or evaluate your strategy, you're interacting with the environment and formulating a strategy as you go. And we know from recent, in the last year, there's been a number of examples where such an approach have been very successful. In health records, you can't really freely experiment with humans, right? That's unethical. And so what we're going to do instead, what we do here is instead of interacting with the human directly, we're going to use offline records and treat the offline records as traces, right? So effectively, imagine there are other doctors that interacted with the patients and created longitudinal traces. And what you're doing is basically learning from these offline traces in order to generalize to you as an individual. Now, one thing that's really interesting here is that for those of you who are actively working on products that involve machine learning or involve AI, there's this sort of segregation. The field has sort of come to this very interesting juncture where people think of these methods as or the field as basically classes of techniques as opposed to an approach. And so when you think of classes of techniques in the sense that they think of AI as deep learning, supervised learning, reinforcement learning, when if you really step way back, a lot of these are effectively techniques where you have strategies for learning. And really, in practical systems, you're using blended strategies very, very often with certain representations that are better suited for your problems. And I'll dive a little bit into interesting representations here that are really important. But when you're going from offline data, when you have large repositories of offline data, and in this case, you have this individual on whom, let's say they're in the health system, you're starting to collect data in addition, right? So you have offline data while this person is in the hospital. T0, you have no other data on them, but as you watch them do people doing things to them, you're starting to collect. So in this particular scenario, it's really a case of like offline to online learning, right? So you're taking data from offline patients, treating them as historical cases, generalizing from those patients to this individual patient, and continually improving your estimate for this given individual based on their data. Okay, and so essentially, in this particular analogy, you rather than interacting with the environment itself, you're doing what in machine learning is also called off-policy evaluation. So effectively, taking offline data sources, generalizing from them as though somebody was interacting with the environment there, using that data to generalize to you. So I gave that very simple high-level analogy. Let me now drive down. So in this particular example, kind of what is my analogy of the game, right? What is my goal? What is the data? What is the representation? So here in this particular case, so I don't have a laser pointer. So on top, what you see is effectively, think of this, so you have a timeline, and those stars are what are called adverse events, right? So think of septic shock as an adverse event. Okay. Now, the second line, what I show you is what's called the latent system state. So what that means is, over there, and this is a cartoon figure, effectively what's happening is the person flat means they're fine, and when that goes up, effectively what it's indicating is this person's getting sicker. And so you're starting to see the fact that the symptoms are coming up before the adverse event happens, right? And then as you get treated, you get better, you go back in, and let's imagine you had a recurring episode, again, you see the symptoms go up. So one of the interesting and super hard things about medical data is that the notion of what is a true gold standard or an annotation itself is really broken. And in defining these goals, we have to think harder about what are we training against. So in this particular scenario, in some fraction of the cases, you observe the adverse event, right? In other fraction of cases, they get treated and you never observe the adverse event at all. So that's principle number one. Second, in the cases that you're observing the adverse event, really the event, like the signs and symptoms or the state that you're really trying to capture, which is human health, is starting to deteriorate way before the event. And your real hope is to uncover that. So what would your desired system output look like? Ideally as follows. So here the system, it says nothing, all is good. And then effectively, just as you're starting to experience the symptoms, it's very, very good at detecting. So it gives a green right from the get-go until it's clear, in which case it subsides and then does. So that's your desired, that's what your ideal system looks like. And now here, in our case, what we're going to do is have a detect output that looks more like the following. Effectively, it's going to say negative if it's sure that this person's fine. It'll have the option to wait and watch. In other words, if I'm not sure if the person is okay or not, I can choose to say nothing, which is this area. And if I say something and I'm wrong, then I mark those areas in red. So here in this case, I think you're fine, so it's green. I think you're getting sick, and I'm wrong, so it's red. Then I decide, I'm not so sure anymore, so I go silent and it's fine, although I take some penalty for waiting and for not sort of catching it. And then I finally catch it, so I'm good again, and so on and so forth. And I think you've recovered, and I think you're... So that's the idea. So here, you're taking data from many, 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 many patients, all that look like this, in order to try to produce, this is the detector output, and your goal is to try to produce that desired detector output. Right? So now let's go back to what's the goal. So here in this case, so here are the three neat tricks, even though I won't dive into these tricks in this talk, but here are the three neat key ideas we'll exploit. So first is, we want to have alerts that optimize the user's objective. So the user's objective is what? Detect this patient as early as possible, but try not to overprescribe. In other words, if you're not sure, I'd prefer for you to wait and watch, right? So there's a cost of a false alert, but ideally I would like you to catch them as early as possible. Now, in order to know when to alert, the objective function relies on estimates that are computed by the machine. And the estimates here are as follows, right? So the estimates here, we jointly model both the data that are coming in real time. And so some of the challenges are, how do you model this kind of spotty data and produce a posterior over what you believe the time to event is, and now you're using that posterior to infer a policy for when to alert. Okay, so that's essentially the three key pieces that tie this together. Okay, so now there are numerous strategies for modeling these. We've developed new variants of the system over the years with different strategies for modeling these, and I'm going to show you sort of a quick peek of some of the challenges here and then some results. So one thing that's hard about modeling this kind of data is the fact that the data comes in very different granularities. So you have things like heart rate, respiratory rate, oxygen saturation that comes out of bedside monitors. These are really frequently recorded samples. And then simultaneously, you have things like lactate measurements, which happen very infrequently and often at the discretion of the care provider. Creatinine, which happens, say, once a day, others that might happen, and these are not on a regular schedule. So typically, outside of healthcare, in our domains like computer vision or NLP, we have this luxury of these are very hard domains too. But some additional complexity that's introduced here is the fact that we have many different types of data. These different data have different sampling granularities, and moreover, some of these are not, you can't use the assumption that they're missing completely at random. They may be missing not at random or missing at random. In other words, you can't assume, there may be systematic bias in when they're missing, right? So when you're doing your generalization, you need to be thinking about that. Okay. Further, so there's, the fact that there's varying, so these are some of the very interesting directions where I think we as a field can go in terms of areas to exploit in trying to make these systems better. Further, the fact that there are interventions, these interventions affect the readings you're reading, and how do you tackle that interaction? In addition to that, you also have notes which contain lots of symptomology. So effectively, what you're looking at is trying to incorporate diverse data sources which have different sources of noise. So in that joint model that I spoke about, you want to think about diverse data sources, different sources of noise, and strategies that allow you to jointly model these data sources with different varying resolutions in order to be able to do that inference, right? And in practice, what strategy you employ is effectively a combination of, like the complexity of inference, if you will, okay? So, but at a high level, you're now trying to take all this data, you're going back to that objective I started with, which is you have a game. Your objective is to minimize, your objective is to create an alerting system that doesn't lead to too many false alerts, but tries to detect individuals as early as possible. And in doing so, you're exploiting this diverse data to be able to make inferences. So let me go back to sort of implementing, so our first prototype implementation of the system we showed, so this is, at the time, sepsis was still, so we were one of the early people to show that it might be possible to take sepsis and think of this in this data-driven way, where septic shock in particular, which is one of the latest stages of sepsis, you might be able to detect it very early and do something. And so in sepsis, people have shown that every hour delay in treatment increases mortality by 7 to 8%. So timing is very critical. And early variant of the system we showed that we could basically detect septic shock an average of 24 hours prior to shock onset, which in the field at the time got a lot of attention because it was exciting that it might be possible to perhaps go in and intervene and do something. Of the patients who were detected, 2/3 more patients, and I say when I use the word more, I mean compared to the standard of care. So 2/3 more patients were detected prior to having any organ dysfunction at all. What this means is these people are much easier and faster to resuscitate if you can catch them prior to them having any organ dysfunction. And then in overall, just using these simple, and we use very simple data-driven strategies for the first variant of the system. 60% increase in detection performance over current standard of care. So this was extremely exciting. This got a lot of medical institutions excited. I got emails, tons and tons of emails from health systems in order to be able to implement such a system. And in practice, in order to make it possible to tolerate, because there's still sort of, while you can detect a lot of patients, if you're throwing a lot of false alerts, that's not palatable. So the joint modeling strategy that I described to you, we use that to be able to increase the positive predictive value of the alert. So by basically modeling the individual data streams more and more precisely, by taking into account structure across these streams, you can effectively make your system more and more reliable and reduce the number of false alerts you're seeing. And so in our data, we've seen anywhere between 100 to 400% increase in true alert rates by exploiting these different inference strategies. So in addition to that, it's not just the fact that we can detect early. In some fraction of these, in some subset of these patients, it's not clear, even if you could detect them, there are a number of strategies you can try. And the question is, what is the right strategy for treatment? And so similarly, we've taken data-driven strategies to be able to estimate at the individual level, can we get an inference for or posterior estimate of what this person's likely response is going to be? And so here what we're getting is, what I'm showing you here in this picture is effectively the mean arterial pressure, which is one of the main signals you're trying to stabilize. And you have two different treatments here, vasopressors and beta blockers, and trying to learn, so fluids, vasopressors, beta blockers, those are all treatments that affect your blood pressure. And what we're showing you here is basically for different doses from a large data set, inferring what is your, each line is an individual, and it's the mean response for a given individual. And effectively, what it's showing you here is that if you give this treatment, how it affects any given individual. So the strategy for being able to take individuals' data as they come and forecast what the likely response to a given treatment would be. And what this then allows us to do, this is this integrated strategy where not only can we detect who are the individuals at risk, we can also try to forecast what are the things they're likely to be responsive to, and essentially build this system that can get this timely treatment to this patient as quickly as possible. So before I go on to talking about deployment a little bit, of course, the strategy is not unique to sepsis. There are numerous other areas of medicine where this notion apply, including some areas that we're pursuing in our lab, scleroderma and lupus, which are chronic diseases, and others in the field are pursuing, such as in hypertension and multiple myeloma. So we built this system. It was so now I'm especially speaking to the individuals who are either like super excited to make an impact and trying to think about, well, I built this beautiful system. Shouldn't it be possible to sort of save patient lives tomorrow, right? And so the question is like, what does it take to So in the last year, we spent time trying to think through, what is it going to take to deploy a system like this in practice? And sort of what are the barriers to adoption? Where are the challenges, right? So as a dreamy-eyed data scientist, we're so excited to be, we need a way by which we translate these interventions into hospitals or into clinics faster. And so here are some things I've learned. So first thing is, you have a life-saving intervention. The question is, you're thinking, why is the health system not running to install your product, right? Like, dude, I can save lives. What's better than that? Like, this has got to be the most exciting thing possible, right? So here's sort of the first sort of, and I very frequently sort of do due diligence for startups or companies who come in, and as sort of someone who works in the field, I'm asked to come in and evaluate. I think most health systems don't even have access to individuals who are necessarily well-versed in the field and can really do evaluations. But so one thing you want to be thinking about as you're approaching health systems or outpatient clinics or these enterprise consumers, if you will, is that to you, your product is a no-brainer. This is so awesome. Why wouldn't you want it, right? Even if there's, don't worry about the fact that there's imagine a world where there is no competition, right? You're not even trying to compete with other people. All you're saying, you're the only product in the market to do something like this, it's going to save lives, it seems like a pretty good idea. So to you, your product is a no-brainer. To them, you're super risky, right? And this is very interesting and specific to healthcare in very unique ways. So in healthcare, the fact is you're dealing with patient data. There are numerous ways to screw up when you're dealing with patient data. So when you're walking in the door, to them, you're a total, source of risk or threat. You come in and you screw up one thing, they're in the front page of, I think it's the New York Times in the US, the corresponding version here, but front page of the New York Times, right? So essentially, it's very important to understand like their psyche when they're evaluating you, right? So you need to think hard about what do they perceive as risks and mitigate those risks. So the fact that you're touching sensitive data, okay? Another, the fact that when you're deploying the system, you're going to be messing with their health system. You're going to be messing with practice within their health system. That's really hard. I'm going to come back to that in a few minutes and talk about things you can do, things to think about there. Second, let's imagine you were able to convince them, right? Like this is cool, you've got published data. Your value proposition has to be really clear and easy to evaluate. It needs to be, for every real person with a real value prop that's approaching them, there are at least 30 other groups or companies that are approaching them that don't understand these ideas, that don't necessarily have the best techniques, that aren't experts in the field, but they're excited by the possibilities, right? And imagine for the health system, for them, they're trying to figure out who is real and who is not. And even if your true positive rate is there's 1 of 30 that are real, right? So you basically have to be, if you let a few in the door, very likely most health systems have had bruises from past experiences, and that's sort of what you're up against, right? I think as a field, we could, so for those of you who are, again, trying to translate products, we can think harder about, I think here the field needs to help you a little bit more too, because we need to think harder about rigorous and clear evaluations, because you're getting paid by your funder, you're in a massive rush all the time, things, like every single day you wake up and you're just trying to basically kind of get something out, you're always behind. There's always a long to-do list and you're always behind. And the question is, you need to somehow cut corners. And the first place you cut corners is in in startup land. Unlike in other areas, in healthcare, data is very important. The rigor and clarity of your data is very important. They still believe in RCTs. And when we take tech, where we're not used to these RCTs, and tech moves really, really fast, and we move it to the world of healthcare, not having rigorous, clean, and clear data becomes really problematic because they don't know what what you're offering them, right? So having rigorous and clear evaluations. And so, 2, this is a new market. They're not used to thinking of software as reliable diagnostics. They're used to thinking of hardware as reliable diagnostics. So for all possible practical reasons, this is something that you're educating them on taking their software seriously, right? Software is IT, it's plumbing, it breaks, right? But here you're sort of going into a land where it's going to influence the practice, right? So educate your user about how to, you have to educate them about how to think about differently about high quality from low quality software. And this is, I think, as a community, we will do this together. Now, third, at present, as researchers in the fields, at present, our habits, we're so spoiled. We're used to writing evaluations that are, we're used to writing papers with one-off evaluations on batch data sets, right? So we basically take historical data sets, we do an evaluation, we write that evaluation in a paper. But if you're looking at health systems, this isn't just now unique to this practice alone. It's just that here data is more important and clear evaluations is very important. But effectively, as practice is changing, maybe there's an epidemic, things change all the time. You need to have a real practical understanding of how that data, how those changes are affecting the quality of your system. Is it suddenly, are you going to expect to see false alert rate go way up because of certain properties in the system? And thinking, coming up with a way to put more science or a practice around this would serve us all well. And robustness to practice variations. This is sort of an area that I think is very interesting and is something that's becoming more clearly, providers are starting to learn about it more. Effectively, you train something in one health system and you take it to a slightly different health system. There are differences in practices. Those have real consequences on the machine learning solutions you're learning. And in research papers, if you're curious, I can point you to them. We've shown, we and others have shown that this can even have negative impacts in the following sense. You could build systems where you end up harming the patient. Your decision support might not help, but hurt the patients, right? So thinking systematically about all this is really important. So I think this area is maturing very quickly, but here are some sort of really important things that sort of I saw as hurdles that we needed to resolve. And in the absence of all this, what's happening right now is like in tech, a lot of disruption happens from little companies, right? So it's little groups of people who work in very tight, who integrate tightly and make progress really, really fast. But the challenge is, if you're a little group without a 15 or 20 or 30-year history, you're seen as a threat or a risk to a health system, right? Because they're kind of seeing you and wondering, are you going to survive in 10 years or 2 years or 5 years? Because if I let you in my door, and first of all, you're going to screw with my data. But let's say you're great, and I love you, and you've convinced me I should trust you. You should be really grateful to those people who believe in you, in this particular field especially. Then the question is, are you going to even be around? Do you have a sustainability model? And if you come in and you mess with my system for 2 to 3 years, it's really problematic if after 3 years you go out of business, right? So those are the sorts of things they're thinking, and you need to think really hard about tackling all those concerns. In the absence of this, what's happening is this, right? So you have these larger companies that don't necessarily sort of have, where basically they see promise and they're playing catch up really quickly, but their catch up doesn't come from data, their catch up comes from marketing. And the marketing looks like this. Do we have any actionable analytics from a big data in the cloud? Yes, the data shows that my productivity plunges whenever you learn new jargon. Unfortunately, that's a researcher interacting with the marketing team. But maybe in-memory computing with blockchain, accelerate your application, will make all the difference. Excellent. So now suddenly the health system guy is totally overwhelmed. He's like, but they look like the big guys. They look like they know what they're doing. The big guys try. The big guys are too slow to innovate. The big guys don't get what they're supposed to get. The whole field is delayed by 2 to 3 to 4 years, right? So that's sort of the unfortunateness of the scenario. Don't get too, hopefully this is, I think these are good things to know because it helps us, if we can work with them and work around them, it'll hopefully make us smarter. Finally, let's imagine you've managed to convince someone, you understand the threats, you managed to educate your user not to get bought into the sort of sequence of jargon words and to believe in you and to work with you. Then here's something that I think a lot of these sort of data-driven products miss, which is the notion of, it's not just building a tool. You need to build a tool that is usable by experts. So effectively, can you integrate it? You need to think hard about workflow. You need to think hard about getting in there, integrating within their workflow. What this means is if you're giving them like a fancy new product that they have to carry around with 5 other things they're used to, they're not going to carry it, right? And this is something that is kind of pretty intuitive when you hear it, but it's something that 99 out of the 100 companies or tech startups don't ever, partially because it's hard, because you don't have access to the health system, but this is something that people often miss. So to wrap it all up, so the good news is so I think these challenges are possible to overcome. You just sort of have to work through them. In the last year, it's been very interesting. So we've sort of developed a real-time system. It's fully integrated within workflow. It took us like a year to work through some of these challenges. We sort of got approval to go live across 5 hospitals. And hopefully very soon it should be sort of, running as we speak. And I want to see, hopefully if it can make a difference. But sort of going back to Mrs. Manny, so we went back and took our a version of our system that we're deploying, went back, ran it through Mrs. Manny's data, and guess what? On Mrs. Manny, we would have discovered that she was deteriorating because of sepsis 12 hours faster than when doctors currently did. If you remember, I said every hour 7 to 8% increase in mortality. that's really exciting. So we've basically, I think we see so many opportunities as we're starting to look at individual cases. We see so many opportunities where we can see, look, we detected this person sooner, you could have done something, and now having a system that is fully within workflow, the providers can now start acting on, I think will really be exciting to see what we learn. And with that, I want to thank my entire team. Thank you.
Thank you very much. That was fascinating. Are there any questions for Suchi? There's a question over here.
Hi. We both 2 questions. Who's first, lady or? I am. Hi, Savi, Stel.
Oh, great. Thank you. Yeah.
Hi. That was really interesting, actually. I think what you were hitting on was the clean data, the observations that are being picked up in the notes in the hospital, looking at refining that, and that 12-hour advance notice is phenomenal. I think, disclaimer here, I'm a clinician by background, and the fact that this lady has just got through the door in the first place is phenomenal in its own right. Lots of, we know about sepsis being a serious problem because so many people die at home. Of all the people that die in hospital, so many are, don't die, and we don't necessarily call them a sepsis, potential sepsis saved. So what's fascinating is the kind of difference, I suppose, machine learning in these clean data versus AI, hopefully one day, in behavior. So why did that clinician, what was special about that clinician that picked up this foot that they couldn't see because it was too dark in the middle of the night? And, did they just think, it's too late, let's just keep this person at home? Or did they think, gaze is a bit off, hair looks a bit, skin speech is a bit not quite. What is that hunch? And that's kind of the AI. That sounds like the really exciting thing in the future.
Yeah, I think we mystify technology too much. So I would say the thing that makes it interesting is, I think it's all painful and all has to be done very carefully. And the thing that is, like the observation you made, right? How do humans integrate data? Like they're expert humans, if you could imagine having augmented. So I learned, so we're starting this machine augmented decision-making initiative at Hopkins. But as we're trying to deploy these systems, what we really want is, the ability for machines and humans to collaborate, for them to see together what is happening, right? So what the machine is very good at is, ideally, taking a lot of this data, culling a lot of the data, putting a piece of data in context with all the other data that exists, right? So I didn't have time to go into too much detail today in the technical side, but the fact that, creatinine is high, well, creatinine is high, is it because of sepsis, or is it because of CKD, or some any other reason, right? There are lots of contexts that matter, right? And so the more we build systems that deeply think, and I don't mean the word deep in the deep neural network sense, I mean deeply in the English sense, thinks about the data, right, in terms of the connections and the effect any single entity has on any other entity. So for instance, the fact that you do an intervention, and how does that intervention affect the 5 other things, which then affects the 5 other things. I think those are the sorts of reasoning you need. That is what gets our clinicians really excited. When we show them, for instance, on an AKI patient, or on a patient when they were given vancomycin, which is an antibiotic, and you can see that, oh my gosh, you are forecasting based on this person's history and what they've had, this person is likely to deteriorate, or this person is likely to get AKI, and you kind of take other context into account. That's exciting to them because it's not just sort of, I guess on the surface gleaning 4 or 5 different indicators and sort of doing averages, right? It's sort of modeling interactions and dynamics. So yeah, so I agree. I think this is very exciting. It's a great field, and I think we've barely scratched the surface.
Thank you. So we're going to take a question over here.
Yeah, hi. Just 2 questions, actually. One is, to what extent did your system, once it was trained, actually pick up new markers of sepsis? That a clinician, given the same data at that time, would not have made the right call, versus what is the benefit actually of just the alerting function? In other words, a lot of this stuff in a system may be, if someone ever looked at all of the data at the right time in context, a clinician would have made the same decision. However, just given the workflow in a hospital, that doesn't happen, and that's why a lot of this stuff is missed.
Right.
So that's my first question. The other one is, you talked a little bit about the biases of some of the data that are collected. Yeah. I wonder how you deal with some of this, and particularly some of these systems in health data where maybe you don't really have a good baseline on most people because they only ever visit a doctor or a hospital when they have something wrong with them, and therefore you're not going to have a baseline of what does healthy normal look like for that person.
They are both great questions. I think we're going to take an answer to one of those because we have, otherwise we're going to run out of time to eat lunch. So we'll just take the first one, please.
So first of all, I apologize when I'm a little over in my talk, but I will be around for lunch and the rest of the day. So I'm happy to answer questions. This is very exciting to me. Okay, so I have to pick one of the two you're saying.
Let's talk about biomarkers. I think that's a particularly interesting question.
Okay, great. So here's, so the question was actually it was a very nice question. How much of it is, if you put a clinician right there in front of the patient, and you had the ability to put a clinician right there in front of the patient at all times, then it would catch. And so I actually think that would go pretty far, in the sense that if you took the best, like if you took expert clinicians, like, you know, some of my collaborators, phenomenal, not some of them, all of them, they're phenomenal. But yeah, if they went and they could stand in front of the patient 24/7, they'd be using their curious minds constantly to figuring out what's going on, and they would likely catch deterioration. So I think a large part of it is being able to monitor patients, many more patients at the level of a super expert clinician with experience more closely. So that's one. The second piece of this, though, is a part of it is that there are our typical practice, in order for us to be able to store these rules in our head, we do tend to look for like some triggers, right? Some things that happen to be triggers, right? Something went suddenly downhill very quickly. Something went, So what I'm basically getting at is often in practice, suspicion rises when some large sudden event happens. But in this scenario, actually, you can see cases where, when you're looking at a large collection of signals, the fact that some subset of them are going out away from the norm in concert is informative, right? So that's not something that I would say typical clinical practice pushes you to do as much. And so if you got an expert clinician and you sat there and you said, look, I really think this person is high risk, something may be wrong, and then you prompt them to go investigate, then they might suggest that, well, are you saying this because of this, and this, right? But on their own, those things are not going to catch their attention.